We now return to the equilibrium of planar bodies and consider two special statically determinate members, the two-force member and the three-force member. A two-force member is a body pin-connected at two locations with no moment loading, no ability to react moments, no distributed loading, and no loads applied at intermediate locations between the pins. By examining force and moment equilibrium for such a body, we will be able to conclude that a two-force member simply transmits a load along a line defined by the two pins. As this figure shows, it doesn't matter how the member is shaped. A curved or angled shape transmits the force between its pinned ends the same as a straight member. We can show that a two-force member has these attributes by considering the general equilibrium of a body with pin-connected ends and no additional loads. As the figure on the lower right shows, we begin with a coordinate system tangent and normal to the line between the pinned ends. Because pins prevent translations in any two mutually orthogonal directions, we begin the analysis with two force reaction components at A and two at B. Imposition of force and moment equilibrium tells us that the normal force components F2 and F4 disappear, and the two tangent components F1 and F3 are equal and opposite to each other. A body with four unknown reaction components is then quickly reduced to a body transmitting a single, yet to be determined force, F. It should also now be apparent why it is important that there be no additional loads on the member. Suppose we have this same member and we need to account for its weight. Moment equilibrium about A will now require the normal force component at B to be non-zero, and then force equilibrium in the normal direction will require the normal force component at A to be non-zero. The same non-zero normal components would develop if the body were loaded by a force couple, a moment, and or supported in a built-in or clamped configuration. Once we have identified a member as a two-force member, there is no need to examine its equilibrium. We used equilibrium already to identify it as a two-force member. All that remains is identifying the magnitude of the force transmitted by the member. This becomes most important in analyzing assemblies of bodies. In our problems, we might be looking at 5 or 6 bodies interacting in a piece of earth-moving equipment. If we had to write equilibrium equations for each of those 6 two-dimensional bodies, we would have a total of 18 equations. It doesn't take long to realize that analyzing even a simple assembly becomes unwieldy if we have to account for all that. If we can begin such an analysis by identifying all the two-force members in the system, then we can greatly reduce the complexity of the problem. As this figure shows, it doesn't matter if the ends of the two force members are connected to more than one other body in the assembly. As long as the member carries only forces transmitted through its pinned ends, it can be represented as a two-force member. Finally, we consider the three-force member. This is a member that has forces applied at 3 points with no moment loading and no distributed forces. Although the two bodies shown here both constitute three-force members, we will most often encounter the one shown at lower left, where the three forces are not parallel. In this case, the three-force member constitutes a concurrent force system, so there is a point where the lines of action of all three forces intersect. Since we can impose moment equilibrium about any convenient point, we can see that imposing moment equilibrium about the point of concurrency indicates that moment equilibrium is identically satisfied, and all that's left is imposition of force equilibrium. Although this may be interesting, I tend not to place nearly as much emphasis on three-force members as I do on two-force members. This is because there generally isn't an efficiency or simplicity associated with identifying a three-force member as such. If we fail to identify a qualified member as a three-force member, we simply apply force and moment equilibrium as we typically do and proceed. If we do identify a qualified member as a three-force member, identifying the point of concurrency in addition to imposing force equilibrium can be just as much work as simply imposing force and moment equilibrium as if it were any other body. The following example contrasts the effort involved with these two different approaches. Here we have an example from earlier in the chapter involving a piece of equipment called a spanner wrench used to apply torque to circular shafts and other similar shapes. We're told the wrench makes contact with the shaft at point A, which may be assumed to be frictionless. What that tells us is that at A we're going to have a normal force where the workpiece pushes back against the spanner wrench, but we won't have any friction force tangent to that workpiece. We're told that at B there's a small pin that fits into a hole in the shaft, and it's through this pin that the wrench is going to be able to exert a torque on the shaft. So we will have both normal and tangential force components at B. We're going to look at this problem now two ways. One, in just the traditional way where we draw the free body diagram and impose force and moment equilibrium. And then since there are three forces applied to this spanner wrench, we could potentially treat it as a three-force member, and we'll see what the contrast is in terms of the amount of work that's involved in getting the solution between a traditional approach and the three-force member approach. So the first thing we're going to do in this problem is just draw free body diagrams of the spanner wrench, and I'm also going to make an attempt to draw the free body diagram of the workpiece just to describe what's happening in this problem. So this will be the workpiece. This won't actually be part of the equilibrium equations that we're going to write, but just to provide some reference. And we're told that this angle alpha for the specific problem under consideration is 120 degrees. So my spanner wrench in this case is going to look something like this. It's going to go all the way around past 90. And over here, this will be a 30-degree angle. Now, what's happening here? So we're applying this force P to the wrench, which is going to impose a counterclockwise torque on the workpiece. So the force P applied to the wrench is going to impose a counterclockwise rotation on the workpiece. The wrench makes contact at A and B, so we'll have a normal force at A and a normal force at B. Neither of those is responsible for a torque because their lines of action go through the center. To impose this counterclockwise rotation on the workpiece, the tangent force at the pin at B will have to act in this direction. We'll then have equal and opposite forces exerted on the wrench. So if the normal force acts as shown on the workpiece, it will act in this direction on the wrench. Same with the normal force at B, and then we'll have equal and opposite force on the spanner wrench. So we'll have FB in this direction, and then we have the force P applied out here at the handle. Now, if you'll notice, the workpiece right now isn't in static equilibrium because there's going to be a torque around the center from the pin at B, and this would ultimately lead to some kind of angular acceleration of the workpiece. What I'm going to show is a moment M that's in the clockwise direction that is acting in the background, and it represents whatever rotational resistance is being offered to the workpiece being turned. So M is in the background. We won't actually be imposing equilibrium on the workpiece, but it's just to provide some perspective of what's going on with the wrench. So I'll call the center of the workpiece O. We'll use a traditional XY coordinate system. And if I write sum of the moments about O equals 0 for the wrench, I have the applied force P acting through the length L minus the friction force at B acting through the workpiece radius is equal to 0. And that gives me that the tangent force at B is equal to P times the ratio of L over R. So one of the things we notice from this result is that the design of the wrench enables us to amplify the force P that we applied at the handle, so that the force that's being applied at B is going to be larger than P by this ratio of L over R, which is presumably much greater than 1. If we sum forces in the X and Y direction, we have NB sine 30 plus FB cosine 30 minus NA equals 0. And in the Y direction, we have NB cosine 30 minus FB sine 30 minus P equals 0. And we'll call these equations 1, 2, and 3 respectively. Using the fact that sine of 30 is a half and cosine 30 is root 3 over 2, we can, from the third equation, write that the normal force at B is equal to 2 over root 3 times 1/2 the force at B plus P. And then, since we've already found FB in terms of P, this looks like P times 2 over root 3 times the quantity 1 plus L over 2R. If we take that result and put it into the second equation, we have NA is equal to P times 1 over root 3, 1 plus L over 2R, plus root 3 over 2 times P times L over R. So these equations and their solution represent the amount of effort we would put in using a traditional approach, drawing a free body diagram, and imposing force and moment equilibrium. And we would now like to contrast that with the three-force member approach. Before we do that, we just want to make some notes about what these results are telling us. And in particular, I'm going to focus on what's happening at the pin location B for reasons that will be apparent, I think, once we take a look at the three-force member approach. So I could write the x component of the force at B as the sum of the x components of the normal force plus the x component of the tangent force, and that sum also is equal to the normal force at A. I could similarly write that the y component of the force at B would be the sum of the y components of the normal force at B and the tangent force, and that this is equal to P. That's just really a different way of looking at the x and y force component equations, because notice that mbx plus fbx is really this term right here, and nby plus fby is this term right here. So I haven't really stated anything new with these equations. I've just essentially looked at the components at B in terms of x and y components instead of tangent and normal components. So we'll just note from this that the ratio of the y component to the x component at B is the ratio of P to NA, but we actually have this expression right here that gives us NA as a multiple of P, and so this ratio actually just depends on geometry. It's 1 divided by 1 over root 3, quantity 1 plus L over 2R, plus root 3 over 2 times L over R. I'm going to multiply and divide this expression by the ratio root 3 over 2R, top and bottom. And when I do this, the term in the denominator can be arranged in such a way that it just turns out to be L plus R over 2, and I have a root 3 over 2 times R in the numerator. So I want to pay attention to this result. This is a result I get from just rearranging what I obtained with the traditional approach. Now, why would I do all that? Let's go back to a free body diagram of the spanner wrench. And now, if I were going to recognize this as a three-force member, I have forces applied at 3 locations. I have the force applied at P here. I've got the normal force at A here, and I've got the force applied at B through the pin at that location. So what am I going to do with this? I have the force applied out here at P, and then I've got my normal force NA. And now what I'm going to note is that the lines of action of P and NA intersect at this location. And so what that tells me is that that point is the point of concurrency for the three forces, and without doing any equilibrium solution, just recognizing this as a three-force member, what I can say is that the line of action that goes through B now will have to also go through that point. And that means that the line of action of B has to lie along this line. So that tells me that B looks like this. And what is the relative size of by and bx? It's the same rise over run I get from this. And what is that rise over run? Well, at an angle of 30 degrees off the vertical, that rise in blue is root 3 over 2 times r. It's cosine 30 times the radius. And in bx, it's L plus r sine 30 degrees, which is L plus r over 2. So recognizing this as a 3/4 member, I right away get this relative size of by and bx. And now if I'm going to proceed with the solution, I would say sum of the forces in x equals 0 and sum of the forces in y equals 0. And that would just give me bx minus na equals 0 and by minus p equals 0. I don't need to impose moment equilibrium because it's already in moment equilibrium by virtue of the fact that it's a concurrent force system. So I have just two force component equations. Two comments about this. The first is it was relatively easy in this problem to identify the point of concurrency, but in many 3/4 problems it's much more challenging than that. So for all the savings and work I might have achieved by not having to write the moment equilibrium equation, I might have that much more work again in just identifying the point of concurrency. It's also the case that in this particular problem, a more natural description of the force components at B would be in terms of directions normal and tangent to the arc made by the spanner wrench. So even though we have these force components Bx and By, they're not in the most physical or intuitive form. So for this combination of reasons, I tend not to put as much focus on 3/4 members. There isn't the same kind of efficiency with this solution approach that there often is when we can identify something as a 2/4 member.